So let's keep going with our look at spectroscopy, and we're on example number 5, mystery molecule now. If we look at our data, of course the infrared, mass spectroscopy and nuclear magnetic resonance. A bit more interesting in the nuclear magnetic resonance this time. Things are a lot more busy than we've seen previously. But again, if we start with the infrared, in at about 2963, we've got that carbon to hydrogen stretch as we would normally expect. Almost impossible to not see that in a organic molecule. And then overlying on top of that is this peak at 2937, a broad peak, which is coming from the OH stretch of a carboxylic acid. We know it's carboxylic because its peak is below 300. If it was just simply an alcohol, would be much closer to maybe about 3200 for the tip of it. So being this far to the right, that strongly suggests a carboxylic acid. And we can see one side of it here running down, and then imagine the other side, which is camouflaged slightly because of the CH stretches which are in there as well. Moving on, we've got the peak at 1712, of course right in the middle of our range, which can only be a carbon to oxygen double bond stretch at 1712. And then down at 1216, we've got the last piece of the puzzle, that carbon to oxygen stretch at 1216. So very much telling us that there's a carboxylic acid in our molecule. Looking at the mass spectroscopy, we've got a molecular ion peak in at 102. And of course, we know from that mass of 102, we have to take into account the 32 grams per mole for the two oxygens, which leaves us with 70 grams for just carbon and hydrogen. Dividing that by 14 would go in neatly 5 times, so C5H10. And then of course, taking into account the two oxygens gives us a formula of C5H10O2, and we're 2 hydrogens short of our normal saturation if there were 5 carbons. Of course, CnH2n plus 2, that would suggest 12 hydrogens, so we're 2 short, which of course can be accounted for with the carbon to oxygen double bond. So the mass spectroscopy fits with our idea that we've got a carboxylic acid. If we move on to the nuclear magnetic resonance, further proof that we've got a carboxylic acid, because way downfield, almost at 12 ppm, we've got that peak at 11.80, which is pretty much solely the range for a hydrogen on a carboxylic acid group. Almost nothing comes close to being that far downfield. The next peak we would see would be maybe on an aldehyde about 10. There's very little which goes that far downfield, unless there are multiple withdrawing effects pushing a peak further downfield than we'd normally expect. After that 1.8, the next peak is at 2.20, which is in the range for a pair of hydrogens which are next door to that carbonyl group, exactly where we would expect it. And because the peak is split into a triplet, we know that these two equivalent hydrogens have next door two hydrogens which are not equivalent. And there they are in green. So the peak at 2.2 for the two hydrogens here, and because it's split into a triplet, that n plus 1 rule, there's two non-equivalent hydrogens next door. And that's the two hydrogens which are causing the peak at 1.46. Very busy peak, as we can see. It's split into a multiplet because it has non-equivalent hydrogens on one side and no doubt another set of non-equivalent hydrogens on the other side, shown in the pink. And so there's a splitting pattern from these two and a separate splitting pattern from these two. And mashed together it gives that big multiplet for the peak at 1.46. For these two hydrogens themselves, they form a big multiplet as well. the peak at 1.22, and you can see why again. Two non-equivalent hydrogens on one side trying to split this into a triplet, and three non-equivalent hydrogens trying to split the peak here into a quartet. And so that would give a big mashup in this multiplet that we see at 1.22. And then finally a peak at 0.78, because that must be the peak for the three hydrogens in the end. And of course their peak is split into a nice clean triplet because they only have two non-equivalent neighbors on their left. And so very nicely we put a jigsaw piece together with all the hydrogens in the carboxylic acid. We've got pentanoic acid.